All right, so this lesson is on summation notation. So when we talk about integrals, and we've talked about Riemann sums, and how integrals can be interpreted as a sum of a whole bunch of little rectangles that would fit underneath the graph, right? The reason why we need to study this in our AP Calculus is because this is a question from a practice exam that's a multiple choice question that you will see. And this question is very clear. It says, which of the following limits represents or is equal to this integral right here? And so what I'm going to teach you today is I'm going to teach you exactly how you get from this to this, or this, or this, this, or this. Does anyone know offhand which one it would be? Any guesses? I'll take a guess right now.
B.
B?
D.
D. Okay. Is there a reason behind that guess, or is that just a random letter that you chose here?
I chose it because it has 3 over n.
You chose it because it has a 3 over n. That's interesting. And?
I would go with B.
What? Keep going with that thought. 3 over n. What is? Why 3 over n? Why did that pique your attention?
The interval is 5 to 2.
The interval
2 to 5,
is
so it's like
2 to 5, and that's 3 units.
Yep.
Okay. Okay. I'll tell you. We're going to come back to this and see if you are right, Jayesh. Okay. There you go. That was your guess. Now, here we go. We have already learned this, that the integral, okay, in this notation right here, is the exact, one of the main applications of an integral is finding area under a graph, right? So this integral from a to b would exactly represent the area under the curve and above the x-axis, starting at a and ending at b, right? Lower limit of integration, upper limit, from the x-axis all the way up to the graph. Or if the graph dips below, it's positive area under above the x-axis and under the graph, and it's negative below. So there would be a collection, an adding of those two, positive and negative, to come up with an overall integral. Now, we've also learned that this is the notation that is the same, okay, that also can be represented this way. So what I want to talk to you about today is how we get from here to here and how we can be sure. So the first thing I want to tell you is this, that when you see a limit of a sum, okay, a limit of a sum, and this is capital S or uppercase S, the Greek letter sigma, and that means summation. So remember that what we've studied is that the Riemann sums are rectangles that would fit underneath the graph that would approximate the area. So we can draw a bunch of rectangles here, and we talked about LRAM and RRAM and MRAM and TRAM, which was like the trapezoid. But if we have, a collection of rectangles like this, we can guess what the area underneath the graph is by adding up the areas of all of the rectangles. So if we let the number of rectangles approach an infinite number of rectangles, that means those rectangles are getting super, super duper small, thin, right? And the width is approaching 0. And so if we take n as it approaches infinity and we add up all of the rectangles starting at the first one and going to the nth one, that's going to be the same as the integral, okay? So that's the same as this part. A limit of a sum means integral. Obviously the function would be the boundary there, the upper or lower boundary, and that's also represented here. Now we have this little x sub k, okay? So x sub k would be the x values that would make either the right side or the left side of the little rectangles. So this would be, x k1, this would be x1, x2, x3, and so on. And so that's why we have this little bit here. And of course the dx, right, kind of represents the width of those rectangles, the differential of x. So what's the difference between one x and the other one? And of course, this is going to, as n approaches infinity, this is going to approach what?
0.
0 is correct. As n, the number of rectangles approaches an infinite number, the width of them is going to approach 0. Perfect. Okay. All right. So let's move on from here. F of xk can also be written as this. Now watch very carefully. We can write this as f of, and remember this is x1, this is x 2, and so on. So we could write it as a, that is the lower limit of integration, this x value, plus some k value times delta x. Or if k is 1, we can take 1 delta x and add it to a, and that's our next x. If we want to go 1, 2 delta x is over, we can, this k was 2. And if k is 3, that's 3 delta x is over. And so we take a and we add the change in x to get the first number, x value. And then we take a and we add 2 delta x's and we get the second x value, and so on. And so notice that I'm going to zoom in here a little bit. When we write it like this, we're actually finding this height as when x is, or when k is 1. And then when k is 2, it's a plus 2 delta x. It's finding this height, and so on. And so this is this LRAM or RRAM? It's RRAM, very good. It's right RRAM, right rectangular approximation. Okay, approximation. So yeah, so this is RRAM, and we'll put that in brackets here because I think that's good to remember. RRAM. We start at f of a, and then we add 1 delta x, then we add 2 delta x's, then we add 3 delta x's to get all of the x values. Now, these x values are going to be used to find the height, right? Because f of xk is the height of each rectangle. Now, moving on from this summation notation, the delta x can also be written as b minus a. So that is the overall, width of the interval divided by the number of triangles that we have that make that up. And we've seen this before too, haven't we? So b minus a divided by the number of triangles, that is the delta x for each of those rectangles. So here we have height, right? This is the height of each rectangle, and this is the what? It's the width. Very good. Which means that this summation notation can be written like this, and please don't freak out. This may look a little more complicated than this one, but we're basically expanding these two, right? We're going to write these just a little bit differently, and this is what this becomes. Okay? So this is sort of the pattern that we're going to use to interpret an integral, and we're going to write it in summation notation as a limit of sums. Okay, so I'll give you a moment to write that down, and then we're going to get a bunch of practice here. We're going to do a bunch of practice questions. Okay, I had a good question. This is different than average value. Yeah, it's not 1 over b minus a. This is Riemann sums. So we're talking about the sums of all the rectangles that would fit, underneath the curve. Okay. All right. So let's get some practice here, and let's take a look. Well, let's take a look at the first interval. Keep that notation up there. All right. So, of course, the integral, right, needs to be written as a limit as n approaches infinity. So we're going to have an infinite number of triangles, and we're going to add up the areas of all of those triangles. So we need a sum notation, and that goes all the way to n. So the integral is represented by the limit of the sum. Now, okay, f of x, I'm going to use square brackets here because I've got to use a number of different little brackets here. But that's going to be f of, now remember it's a plus b minus a over n times k. So what's a? A is 0. There's a right here. See? That's a. So we put a, that's 0, plus, what's b minus a? Well, 4 minus 0 is 4 over n. So again, in order to get the width of the rectangles, we need to take the whole interval, 4, and divide it by n. And along the way, we're going to have one triangle, then 2, then 3, then 4, then a billion, then a trillion, and then near infinite, right, as they get smaller and smaller. So as n approaches infinity, the width is going to approach 0, but it's going to be 4 over n wide. And then we just write a k there. You can write a k beside or up with the 4. You'll mostly see it up with the 4 there. Okay? So that's going to be our height. And then the delta x part is going to be simply 4 over n. And you can put brackets there if you want. Okay, so that's the summation notation for that integral. Does anyone have any questions about that? I'll answer one obvious question. Yes, you could just write this as f of 4kn. You don't have to put the 0 plus, but just for teaching you how this, let's follow the pattern, okay? All right, let's do another one. The second one here is an integral from 2 to 9. So the integral, we have to write limit as n approaches infinity of the sum k equals 1 to n. And we're going to do the function evaluated at a. Now what's a? 2 plus b minus a, that's 7 over n times k, or 7k over n. Okay, so this is what's going to replace the x here, right? It's going to be the input variable. And then here we have 7 over n as our width. Question?
K is always 1.
K is always 1. Okay, very good question. The answer is yes. And let me explain why. It doesn't matter what the limits are because K represents the triangles, or the rectangles, sorry. So the first rectangle would have a height of this much and a width of this much. The second one, when K equals 2, would have a height of this and a width of this. So K comes from, again, just one more time, if we go back here, right, K really is so this is the first triangle. K is 1. So you take A and you add 1 delta x. You go up, you find the height, that's the height, okay? And then when K, so K always starts at 1. And that's basically taking your first rectangle, then adding the second, the area of the third, area of the fourth, area of the fifth. So K is always 1, it always goes to n. Yes. Good question. All right, so does this look good? I'm happy with that. Does that look good? All right. Okay, why don't you guys try example 3 on your own. This is similar to 1 and 2. You guys try 3 and I will show you the answer in a second. Go ahead and give 3 a try or see what that looks like. All right, so here's the answer I got. And again, we have a difference of 3 minus negative 2. That's 5. 5 units from A to B. And so we're going to have 5 over n here. We're going to have 5k over n here and so on. And of course, this is A. So that's what the answer for that one looks like. That's summation notation for that. Okay, hopefully you're getting this so far. We're going to make the jump now, and instead of writing this f of, whatever, we're going to actually put that input into the actual equation now, or into the actual function. So let's substitute the actual function now into the summation notations. This is how we would do example 4. Okay, so of course we have an integral, so that is the limit as n approaches infinity of the summation of rectangles from the first k rectangle, k1 to n. And now instead of doing f of x, we're going to actually use this equation. So what do we have for an a value? Well, that's just 0. So you could put 0 in there if you want. Plus, what's b minus a? 4k over n. Right? And that's going to be to the power of, right, so you can use whatever brackets you want here. I'll use 2 sets of brackets. So that's going to be to the power of 4. And outside we're going to have 4 over n as our delta x. Okay? So do you need the 2 sets of brackets? No, not exactly. But usually I'm going to use a set of square brackets there because there's, well, you'll see a little bit later here. So I would be okay with this, right, without the brackets if you want. Just have to make sure that you have a second set of brackets or some kind of multiplication there. Okay. Okay, so this one, example 5 here now. So limit as n approaches infinity of the sum, k equals 1 to n. All right, so let's examine this here now. The input is over here, the x. So we're going to have, and there we go, I'll use my square brackets now. Make that messy. So we're going to have 3. Now, what are we going to put in for the input variable? Well, that has to be a plus k delta x, right? So that's going to be 2 plus What's the range here, or the sort of the interval? 9 minus 2 is 7. So 7k over n squared times 7 over n. So hopefully we're able to see this. Here's the function, and there's the function. What's the input variable? Well, it's going to be 2 plus 7 over n times 1 for the first height of the first rectangle. Then it's going to be 2, the next x is going to be 2 plus 7 over n times 2. So it's 2 delta x's, and then you take the height there, that's the height. Then 3 delta x's, take the height. 4 delta x's, take the height, right? So this is what it looks like with the function actually substituted. We good there? Any questions? Okay, like I say, I've got lots of examples here, so we're going to do several more. I think what I'll do, let's see, what do I have here? Yeah, why don't you guys try this one on your own now? So try this one on your own, take what we've done in the first 2 examples there, and try this one on your own. All right, so here's the answer for example 6. That's what it looks like. And hopefully, again, you're able to recognize the function in there. 2 times, here's x, right, plus 9. And x is going to be a plus b minus a over n times k. So I had a couple good questions while you guys were working on this. The first one is, isn't this, if we're talking about Riemann sums, isn't this just an approximation? Right? Or isn't it going to be either an overcounting or an undercounting? Well, if n is a discrete number, if n is an actual number of rectangles, like any number of rectangles, yes, it won't be exact. But if those number of rectangles approach an infinite number of rectangles, meaning that the width of those approaches 0, and that the overcounting or undercounting approaches 0 as well, right? It almost becomes a straight line. So it becomes a straight line that's almost dimensionless here, right? If we have an infinite number of them, which means that it's completely filled in, it's completely solid underneath the curve. And so that's why if we let the number of rectangles approach infinity right here, that's when this is equal to this. And the other question was, don't we use antiderivatives to figure this out? And yes, to find the exact answer, you can use your antiderivatives just like we did in lessons before to find this actual value. This is another way of expressing it. Okay? So how do you work this to find the answer? You don't really, because you can't actually add up an infinite number of anything, right? So we're not actually finding a value directly from this. We are going to be converting this to an integral and then calculating its value. Okay? But again, this is the notation. Remember that the title of this lesson was Summation Notation for Riemann Sums. So I need you to understand what this integral looks like in summation notation and vice versa. Okay? Is it starting to make a little sense there now? I know you guys probably have a lot of questions. All right. Another thing I'd like to point out, and you'll see a lot in, and I don't know if this particular question, okay, this particular one used K, but in your textbook and in a lot of different areas, places, you'll see I instead of K. So I have a couple more just examples for you where I show you that this does not have to be K, it can be I. And you'll see that, I think, in some of the textbooks that you're going to be using. You'll see I instead of K. It's exactly the same. Okay? It's exactly the same. All right? So this right here, let's work backwards now, and let's write this as the integral. Okay? So what can we pick? Well, I know that this is what? That means integral. Okay? What else do I know? How can I piece things together? I need A and B. I need a function, dx. So how can I fill in these blanks given what I'm given here? Any ideas? Where do we want to start?
You go back.
Sorry?
Go backwards.
Okay, tell me. What do I do? What can I put in next?
You find you can see that we can go to the A first.
A, thank you. You're going to want to start at A. Very, very good. Now, where is it in here? It looks like right there. Okay, very, very good. So I'm going to put 3 right here because that's what A is. Now, how do I know what B is, though? That's really tough, isn't it?
Because of the 3 over n.
Yeah.
Oh, thank you.
Welcome.
This right here is B minus A. So B minus 3 has to be,
6.
okay, well, this has got to equal 3, so B equals 6. So A is 3, and it lasts, the interval is 3 units long. Now, maybe for this example, I could have chosen different numbers here, but to make that confusing, but this is 6. You're absolutely right. Okay, so again, this is A, and this is the width of the interval, right? It's 3 units, so starting at 3, going to 6. All right, so now we need to pick out of here what is the function. Remember, this is the input. So what should I write here? Root 2x plus 1. 2 root 2, this is x plus 1. Okay? Very good. That's perfect. All right. So let's do another couple examples here. Let's do another couple. This one looks very different, doesn't it, than these ones we've been doing. So it's missing some pieces here, which either is going to make it a little bit trickier or a little bit easier. All right? So let's find out what the pieces are. So again, this means integral. Okay, all right, integral. Where's the A?
3.
Okay, I heard a 3, and I heard a
Oh, no,
A 0.
I was looking at a different one.
A 3 or a 0. So what's it going to be? Now, this looks like delta x to me, right? This looks like f of x. There's no x in there. And there's no, 0 plus. We know that the interval width is 5. And so if there's no a plus whatever, blah, blah, blah in there. Yeah. A is 0 and it goes to 5. Okay. Well, I'm gonna go. Sorry, what?
Would it just be 3x dx then?
Okay, so what comes next? Actually, I'm going to come back to these. Okay, I'm going to come back to this. I have to come back to this, and you'll see why in a second. I didn't actually plan to go this way for this one. So yeah, the function here? There's just a constant. So this is actually just a constant function. There's no x's. There's no variable. Dx. Okay. Now, I said I would come back to the limits of integration. Because there's no x in here, this is sort of the situation where, well, and if you were to graph this is y equals 3, right? And so from 0 to 5, that's going to be the exact same as -1 to 4. Or the exact same as from 5 to 10. So you don't really know what these are, to tell you the truth, with this example. So this would be an okay guess, but it could be from 0 to 5, it could be from 10 to 15, it could be from -32 to -27, right? We don't know. So those limits are just kind of guesses. We don't have an indication from here. So is it easier or more difficult? I don't know. Good question. All right, I think this is my last example that we're going to work through together. Then I'm going to give you an activity and an assignment. All right, so for this one here, let's do one more. Let's write this as an integral. Integral of, what's A? What's A here? What's B?
0.
Because the interval width is 2, so that's got to be 0, correct? What does the function look like? X cubed dx. Wonderful. That is absolutely wonderful. Good job. Okay. Beautiful. All right. Any questions about those examples? Any questions about what we've done here so far? Let's run back to this question here. We had one guess of D. I see some hands clapping here. All right, so we've got x squared. We've got an interval of 3. We've got an a value of 2. So I'm seeing a values of 2 here. That's great. Everything needs to be squared. We definitely don't want, is the interval, how many units do we say? 3. So it's not 1, right? So it's not a, because this would be an interval of 1 unit long. It's got to be 3 units. So it's not 1 over here. Okay, so is it this one or is it this one? Yeah, we're missing something right there. So D, Jayesh B, you have gotten it correct. Thank you very much. That was a great guess. Good job. Okay, but I think you said B actually, and not D. Yeah. Oh, you said D. Sounded like B a little bit. Okay. I thought I heard. Yeah, maybe it was B. Hey. Okay. So this is what you have in front of you now. You have two sheets. I'm not going to cut these up into cards and leave them as sheets. What I need you to do is I need you in pairs to try and connect these integrals with these limits. Okay? So try and connect them on a separate piece of paper. You're going to put number 1 goes with number 1 H or number 1 E. Just write the pairs. Take a few moments to do this. And again, what's that? Yes, you can write on those notes. Yeah, but try not to write on these pages. I'll probably use these again. So these are the 10 integrals on this page. Here are the 10 limits on the next page. Okay, go ahead and take a few minutes and do this activity. Okay, so here's the solutions to the matching. You can double check there. Yeah, I'll get those sheets back, the selectivity. Yeah, you can hand those back in. And I'm going to hand out to you this handout, including questions like this, just some activity questions. So each of you will get one of those.